Welcome to the inverse Laplace transform of an exponential times g of s. So recall that the Laplace transform of a step function u of t minus tau times f of t was equal to e to the negative tau s times the Laplace transform of f of t plus tau. So now let's go ahead and define a new function. Let's define g of t as f of t plus tau. Then we can do a little bit of a change of variable. Actually, let's define, we can do a little change of variable. If we set x equal to t plus tau, then we have t as x minus tau. And so we get that g of x minus tau is f of x. And then we can rename it again. So renaming again, we get g of t minus tau is the same thing as our f of t. So then what we get is we get an equivalent statement for the Laplace transform, which says if we have Laplace transform of u of t minus tau times g of t minus tau, this is equal to e to the negative tau times s times the Laplace transform of g of t. This is more useful for doing inverse Laplace transforms. I'm going to give myself a little more space so we can write one more line. So if we, instead of writing things as the Laplace transform of g, let's go ahead and set capital G of s to be the Laplace transform of g of t. Then we have g of t is the inverse Laplace transform of capital G. And so this becomes essentially the inverse Laplace transform of e to the negative tau s times capital G of s is equal to u of t minus tau times the inverse Laplace transform of g evaluated at t minus tau. So this is an alternative way we can use for finding inverse Laplace transforms. Essentially, we take the inverse Laplace transform and then do our transformation after, instead of having to manipulate the transformation sort of as we go through. So this is just a useful trick to use. So let's say we want to find the inverse Laplace transform of f of s is equal to e to the negative 8s times 5 over s squared plus 4. So this 5 over s squared plus 4 is going to act as my capital G of s. E to the negative s, or e to the negative 8s, that means we're working with tau is equal to 8. And so we know that when we take this inverse Laplace transform, that we should have, this is the inverse Laplace transform of e to the negative 8s times g of s. So we know that we should have u of t minus 8, our step function shifted over to 8. And then we should multiply by the inverse Laplace transform of g evaluated at t minus 8. So what we need to do now is find the inverse Laplace transform of 5 over s squared plus 4. So the inverse Laplace transform of 5 over s squared plus 4. This is just 5 times the inverse Laplace transform of 1 over s squared plus 2 squared. And then to make this a recognizable form, we actually need a 2 up top. That will be an omega over s squared plus omega form. So we need a 2 up top, which means we need to cancel that out by dividing by 2 up front. So we have 5 halves times the inverse Laplace transform of 2 over s squared plus 2 squared. I need to give myself a little bit more space. So this is our inverse Laplace transform of g, of course. So we are looking at 5 halves times the inverse Laplace transform of 2 over s squared plus 2 squared. That is just sine of 2t. So we get the inverse Laplace transform of g is 5 halves times sine of 2t. And then, of course, we want this evaluated at t minus 8. So the inverse Laplace transform of g evaluated at t minus 8 would be 5 halves times sine of 2, and then we're going to replace t with t minus 8. So we get that our final answer then is that our inverse Laplace transform of our capital F of s is equal to u of t minus 8 times 5 halves sine of 2t minus 16 essentially. Or we can rewrite this as 5 halves u of t minus 8 times sine of 2t minus 16. So this is finding the inverse Laplace transform of that sort of simple, just exponential times a rational expression. Again, we can also write this in alternative format. We could write this as 5 halves times u sub 8 of t times sine of 2t minus 6 or minus 16. Both of these are completely acceptable forms. So sometimes we see the step functions labeled with a subscript just of where it switches to 1. And sometimes we just stick with that basic switching at 0 and then do translation. All right, let's go ahead and do one more example. This time around, our capital F of s is e to the negative 3s times 1 over s squared minus 4s plus e to the negative 5s times 2 over s squared. Actually, before we do that, sorry, let's write this first one just as a piecewise function. So we have f of t is equal to, it's 0 for t less than 8, and then it would just be that 5 halves sine of 2t minus 16 once we pass 8. Sorry about that. So writing it as a piecewise function, we're 0 until we hit that step function at 8, where we switch up to the function that we have. All right, now let's do this new one. Capital F of s is e to the negative 3s times, in parentheses, 1 over s squared minus 4s, end parentheses, and then plus e to the negative 5s times 2 over s squared. So if we want to take this inverse Laplace transform, we have 2 different exponentials. We're going to work with 2 different pieces. So we'll work with this e to the negative 3s times 1 over s squared minus 4s. And then we'll work separately with e to the negative 5s times 2 over s squared. So let's first take the inverse Laplace transform of e to the negative 3s times 1 over s squared minus 4 over s. So we know right off the bat here we have that our tau is 3. Our capital G of s is 1 over s squared minus 4 over s. So if we set lowercase g of t to be the inverse Laplace transform of g of s, so this would be 1 over s squared is the inverse Laplace transform of, or we goes to t when we do the inverse Laplace transform. 1 over s goes to 1, so we just have t minus 4. So this is our g of t. We know that our inverse Laplace transform becomes the step function times the inverse Laplace transform shifted. So we get this inverse Laplace transform of e to the negative 3s times 1 over s squared minus 4 over s is equal to u of t minus 3 times g of lowercase g of t minus 3. So we take the inverse Laplace transform of our capital G, and then we translate it. So we have u of t minus 3. Then we are multiplying by g of t. We did t minus 4. So we have our blank minus 4, and we will plug in that t minus 3 into our blank. And so we have u of t minus 3 times, we have t minus 7. So that's the first part of our inverse Laplace transform. Similarly, we need to find the inverse Laplace transform of e to the negative 5s times 2 over s squared. So let's do the inverse Laplace transform of e to the negative 5s times 2 over s squared. So this time around, my tau is 5, and my capital G of s is 2 over s squared. So I have the g of t, lowercase g of t, is the inverse Laplace transform of 2 over s squared. And that is actually just 2 times t. So we know that our inverse Laplace transform of e to the negative 5s times 2 over s squared is our step function u of t minus 5 multiplying lowercase g of t minus 5. So we have u of t minus 5 times g of t, in this case, was just 2 times t. So we would have 2 times blank. And into the blank, we plug our t minus 5 since we want a g of t minus 5. So putting together our total inverse Laplace transform of f of s, the inverse Laplace transform of capital F of s, is just these two added together. So we have u of t minus 3 times t minus 7. And then we have plus u of t minus 5 times, that would be 2t minus 10. Oops, I need to update my screen. I apologize. So updating my screen, I now have the u of t minus 5 times 2t minus 10. So if we wanted to write this as a piecewise function, we have that the inverse Laplace transform of capital F of x should be equal to our step. We don't have any component of the function without a step function. So we start off as 0. Our first step is at 3. So we would be 0 for t less than 3. Then from 3 to 5, our next step. So from 3 to 5, our function is just equal to t minus 7. And then once we get 5, both of those parts of the function are visible. So for t greater than or equal to 5, we would have t minus 7 from the first component, plus we would have 2t minus 10 from the second component. Again, for t greater than or equal to 5, both u of t minus 3 and u of t minus 5 would be equal to 1. So we would have both components. And so we wind up getting that our piecewise function is 0 for t less than 3, t minus 7 for 3 less than or equal to t less than 5, and then 3t minus 17 for t greater than or equal to 5. So make sure when you view your step functions, keep in mind that those step functions are kind of tagging onto each other. They're piling up. So that first step function is the initial, well, we have 0 before the first step. Then the first step, we just have that single function. But then the next step, we have to add those two. If we had another step, we would have to add those 3, etc. So here is the piecewise function that we wind up with, taking the Laplace transform of our f of s with a couple different exponentials involved.